Chemistry, Unit 3, Faraday's Law. By Faraday, I mean this wonderful scientist. Okay, so in this session, we'll learn how to use stoichiometry and Faraday's laws to determine the amount of products or times or current for a particular electrolytic process. Okay, well, what is Faraday's law and what does it say? Okay, so basically, Faraday's law in chemistry, what it does is it captures the relationship between the amount of product produced by the electrolytic cell and connect it with the size of the current and the operating time of the cell. How do they connect? Well, very simple. They're equal to each other. What does that mean? It basically says that the amount of electrical energy produced by the power source in the form of a current delivered to the cathode of the cell, and all that electrical current, electrical charge, should equal to the amount of charges gained at the cathode in the reduction reaction. So it's like a law of conservation of not mass, but electrical charges. If you think about it, the electric charge coming from the negative end of the power source shouldn't be lost or shouldn't be destroyed, and all of it ideally should arrive at the cathode or the negative end of the electrolytic cell and be gained by the strongest oxidant there, right? There shouldn't be any loss. Of course, in reality, there will definitely be some loss to the resistance turning into heat, but theoretically, in an ideal process, they should equal to each other. The electric charge provided should equal to the electric charges gained by the cell. Now, so how do we measure the charges provided by a power source? Well, the electric charge in Coulomb, measured in Coulomb, that's the unit for it, passing through a cell can be measured by the current, measured in ampere, and the time, measured in second. And the relationship is when you multiply the current by the time, that gives you the overall amount of electric charges supplied by your power source. That's the supply side. So what happened to the demand side? Well, charges gained at cathode, that must be having something to do with the reduction reaction there, right? So the strongest oxidant gains electrons and be reduced there. Therefore, we just need to connect the amount of electrons being gained to the amount of charges. And the quantity that links these two, the amount of electrons and the amount of charges, is the Faraday's constant. It's given as 96,500 coulomb per mole. That means 1 mole of electron will produce this much coulomb of electrical charge. That number is on your data book. So let's connect the two. The amount of electric charge produced by the electric current should be equal to the amount of charges gained at the cathode. So we have the provider, we have the consumer, and what is provided should be what is consumed. So Q equals to Q, that gives us this equation. Now on the left-hand side, we have the provider, the charges provided over time, and on the right-hand side, we have the amount of electrons being gained, and overall, they should equal in terms of energy. Okay. Well, how does this link to us finding out how much products can be produced and in electrolysis? That is, if you have electron, the amount of electrons being gained should be proportional to the amount of products produced at cathode. and they should in proportion according to their stoichiometry ratios, right? If it's 1 to 1, or if it's 1 to 2, 1 to 3, depending on your normally metal cations, how many of them can gain how many electrons. Okay. So let's look at one example. This is a silver plating cell, which means they are electroplating whatever is connected at the cathode with silver metal. So they'll probably need a silver solution, and then the silver cation can gain electrons at cathode to become silver metal and be deposited at the cathode, right? So they're operating it with a current of 30A and for 20 minutes. What is the mass of silver plated on the cathode? Okay, you should be able to predict it. Well, think about it. The amount of charges provided as current should equal to the amount of charges gained in the form of electrons. So we have that equation, and I equals 30. T is measured in seconds, remember? So we got to convert it to 1200 seconds. And then F is a constant, so you don't have to worry about that. So the only thing that we don't know is the amount of electrons that's gained. Well, we can figure it out easily by rearranging this equation. And the amount of electrons gained is 0.373 mole. And then we have our second stage of calculation. So this amount of mole of electrons are gained by silver, according to this equation. How many silver can be found at cathode? Well, if one silver gaining one electron to produce one silver atom, then if we have 0.373 mole, will result in 0.373 mole of silver metals. Yeah? And then we simply need to do a conversion between mole and mass to find out that at the end, the silver plated should be 40.3 grams.